Welcome back, everyone, to the deep dive.
hmm
Today, we're going to be looking at, well, I guess you could call it a revolution happening right now in AI.
Yeah, I think revolution is probably the right word for it.
With these powerful large language models emerging
No.
and what they're making possible with intelligent agents, we're not talking about just simple chatbots here.
Right. Right.
These are systems, that are starting to reason in really complex ways,
Yeah.
perceive the world around them in more and more sophisticated ways,
Yeah.
and even act on all that information.
Yeah. They can take action across a really wide range of tasks, like much more than we've seen before.
Right. And for this deep dive, we've really gone broad with the research. We're looking at cognitive science, neuroscience, and of course, all the latest computational research. And our goal for you, the listener, is to try and distill the core principles.
Yeah. The essence of how these things are built.
How they're built, how we measure their abilities, and also the really cool ways that they're constantly improving.
Yeah. They're always getting better.
And we don't want to bog you down with, a bunch of technical details, just the essential.
Right. We want to make it understandable.
So, we're going to really try to explain how these agents work at a fundamental level, how they learn, how they collaborate, and then also the really important considerations for making sure that they stay safe and beneficial.
Yeah. Safety is a big one.
And one thing that really jumped out at us from all this research is how the design of this really advanced AI is starting to be inspired by the human brain.
Oh,
Like different components of these systems, they mirror our cognitive abilities, our perception, even emotion-like systems. It's almost like nature's ultimate intelligence is becoming the blueprint.
it is. It is.
Yeah.
I mean, it makes sense in a way, right? I mean, we're trying to build something that is intelligent,
Hmm.
and the best example we have is the human brain.
Right.
So, yeah, there's a lot of inspiration being drawn from that. And I think that's one of the most fascinating things about this whole field.
So, okay, let's unpack that a little bit.
Okay, sure.
This whole brain-inspired architecture, what does that actually mean?
Well, what's really interesting is that the research is showing this move towards a modular design for these intelligent agents, and it directly relates to specific areas of the human brain. So think of it this way. The agent's ability to think and plan, that's being linked to like the functions we associate with our frontal lobe.
Okay.
Then you have like motor control and coordination, and that's kind of like the cerebellum in the brain. And then even more fundamental operational aspects, those are kind of like the brainstem.
Okay.
So it's almost like they're trying to map different parts of the AI agent's architecture to different parts of the human brain.
So it's not just this like mysterious black box algorithm anymore. We're actually seeing efforts to structure these agents in a way that echoes how our own minds are organized.
Exactly. And within that structure, you have these core components.
Right.
So let's start with memory. Our sources emphasize that these agents are going beyond simple data storage.
Okay.
They're really trying to emulate the complexity of human memory.
Interesting.
So, you have short-term memory, long-term memory, but you also have different types of memory, right? You have sensory memory, episodic memory, semantic memory, procedural memory.
And just to remind our listeners, what are some examples of those different types of memory?
Sure. So sensory memory is like, what you just saw or heard. Episodic memory is memory of events, like, your last vacation.
Mm-hmm.
Semantic memory is more like factual knowledge, like knowing that Paris is the capital of France.
Okay.
And procedural memory is knowing how to do things, like riding a bike.
Right, right.
And so they're building these different types of memory into these AI agents.
And so what's the advantage of that? Why do they need all these different types of memory?
Well, it's all about how they learn and act, right?
Okay.
So these agents, they take in all this raw information from the environment,
Right.
and then they have to transform it into structured knowledge that they can actually use.
Okay.
And the different types of memory help them do that.
I see.
And what's really cool is we're actually seeing concrete examples of these memory systems in specific AI agents.
Oh, wow.
So it's not just theoretical.
So they're actually building this stuff.
Yeah, they're actually building it. And
Yeah.
and the key insight here is that these agents, they're not just retrieving data, they're mimicking this complex human memory system.
Yeah.
And that allows them to learn from their experiences and then apply that knowledge in all these really nuanced ways. And that's really a big step forward for AI, I think.
That makes sense. You can't really reason or act effectively if you can't remember past experiences or the things you've learned. So they have
Right.
memory
Right.
and they have this ability to understand their environment, right?
hmm
So how do they actually use that memory to make sense of the world around them?
Well, that brings us to this really interesting concept called world modeling.
Okay.
So the basic idea, and it's actually inspired by this notion of quote unquote small scale models of reality, is that these agents, they build internal representations of their environment.
Okay, so they create a model of the world inside their system.
Yeah, exactly. It's like their own little virtual world. And this allows them to simulate like potential outcomes, reason about different scenarios, and make predictions about what might happen next.
Okay.
And our sources talk about four main ways that they're building these world models.
Okay.
So you have implicit models, where the model learns the dynamics of the world without any explicit rules.
Yeah.
You have explicit models, where they actually try to directly represent those rules and dynamics. You have simulator-based models, which are often used in robotics, where agents learn by interacting with either virtual or real environments. And then you have hybrid approaches, which kind of combine elements of all of those.
So it sounds like a really delicate balancing act, right?
It is.
Like, how do they even figure out how detailed these models need to be?
Right, because the more complex the model, the more computationally expensive it is.
Yeah.
But if it's not complex enough, then it might not be able to make accurate predictions.
Right.
So there's this constant trade-off between complexity and accuracy. And another really important point that our sources make is that memory isn't just this separate thing.
Okay.
It has to be integrated with the world model.
Mm-hmm.
So, your past experiences and knowledge, those directly shape how you understand and predict the future.
Right, right. So it all ties together.
Exactly.
Okay, so they have this memory and they have this way of understanding their environment, but what drives them? What motivates them?
Right. That's where reward processing comes in.
Okay.
So our sources actually draw a parallel here between, the agent's internal reward pathways and the human brain's mesolimbic system,
Which is
which is involved in pleasure and motivation.
okay.
But they also point out some really important differences.
Like,
well, agent rewards, they're programmed,
okay,
right?
okay.
And they're more transparent than, our often unconscious human reward system.
So instead of feelings like joy or disappointment, it's more about achieving, specific digital objectives.
Yeah, in a simplified sense, yes.
Okay.
But there are actually different approaches to designing these reward systems.
Okay.
So you have extrinsic rewards, which are tied to, specific tasks like earning points in a game. And then you have intrinsic rewards, which are kind of generated internally.
Okay. And what would be an example of an intrinsic reward?
So curiosity-driven rewards, those encourage the agent to explore new situations. Or information gain rewards, those incentivize actions that lead to the agent learning more and reducing uncertainty.
Okay. Okay. Interesting.
And, a key takeaway here is that it can be really hard to perfectly translate, human intentions into these AI objectives.
Right.
There's always this risk of what they call reward misspecification, which means that, you could end up with an AI that is optimizing for the wrong thing.
Right, because it wasn't programmed correctly.
Exactly.
Yeah,
that could lead to all sorts of unintended consequences.
Right, right. Now, this idea of emotion-like systems in AI agents, that's intriguing,
Yeah.
but I think it might raise some eyebrows. So what's the reasoning behind that?
Well, our sources explain that there's this growing movement to actually incorporate theories of emotion into these large language model agents.
Really?
Yeah.
Yeah.
And it's not about giving the AI like real feelings or anything like that.
Okay.
It's more about creating more coherent and predictable behavior.
Okay.
So the potential benefits are things like, more consistent moods in the agent's responses.
Okay.
And better interpretability, like being able to understand why an agent might act in a certain way.
Okay.
So it's less about creating a sad robot
Uh-huh.
and more about, developing an AI that can, for example, maintain a helpful and positive tone or respond appropriately to, emotional cues in the data it's processing.
So it's more about creating internal states that influence behavior in a consistent and interpretable way rather than giving them genuine emotions.
Exactly. It's about making them more reliable and understandable.
Okay, so how about perception?
Right. Perception.
How do these agents actually perceive the world around them?
So our sources point out that, human perception is limited by our biology, right?
Yeah.
But AI can process sensory information at incredibly high speeds.
Right.
It's limited more by the power of the hardware.
Okay, that makes sense.
And one of the really interesting things happening here is the development of what are called cross-modal models.
Cross-modal, meaning like they can understand different types of sensory input at the same time.
Exactly. So you have models that are being developed that can integrate text and images, text and audio, and even combine audio, vision, and language.
Wow.
So imagine you see a dog barking.
Okay.
A regular AI might only understand the picture or the sound, but a cross-modal AI could understand that the picture and the sound are both coming from that same dog.
Oh, I see. So it's combining those different senses.
Exactly. It's fusing those different types of information to get a more complete picture of the world.
So an agent could see an image, hear a sound, and read a description, and then combine all of that to get a much richer understanding.
Yeah, that's the goal.
Wow.
And to improve this perception even further, they're using things like human-in-the-loop systems, where human feedback helps to refine the agent's understanding.
Okay.
And they're also developing methods to, filter and improve the agent's outputs. And we also see that the sheer scale of these models, how big they are and the advanced hardware they run on, that really has a big impact on how effectively they can perceive and process information.
So bigger and faster often leads to more sophisticated perception.
Yeah, pretty much.
Okay. Now let's talk about the other side of the coin. How do these agents actually take action in the world?
Right. Well, that's the role of the action system. And our sources, they define this as how the agent interacts with its environment.
Okay.
So they talk about all these different approaches to how agents learn to act.
Right.
You have in-context learning, where they learn from the instructions given in the prompt. You have supervised training, where they learn from labeled examples of actions and outcomes. And then you have reinforcement learning, which is where they learn through trial and error, guided by rewards.
And reinforcement learning is particularly important for letting these agents act on their own, right?
Exactly. It's a key part of enabling autonomous action.
Okay. Now, what about this idea of tool-based action?
Ah, yes. This is a really significant paradigm where these agents, they actually learn to utilize external tools to enhance their capabilities.
So tools like what?
Well, they could be specialized tools for scientific research or even more general-purpose software.
Okay.
The idea is to extend the agent's own internal abilities by giving it access to a wider range of resources and functionality. It's like, how we use tools in our own lives to solve problems.
Right.
So instead of trying to know everything and do everything itself, the agent learns to identify and use the appropriate tool for a given task.
It's like a scientist using a specific instrument for an experiment.
Exactly.
Okay, so instead of trying to know everything themselves, they can learn to use the right tool for the job.
Right. They become more versatile and efficient that way.
Okay. So now let's shift gears a bit and talk about how these intelligent agents actually improve over time.
Right. Self-evolution.
Self-evolution, yeah. Our sources really go into depth about that.
Yeah.
So this sounds a bit like AI becoming self-aware and deciding to upgrade itself. Is that what's happening?
Not quite in that science fiction sense.
Okay.
It's more about this transition from AI systems that were, painstakingly designed by humans to systems that can actually learn and optimize themselves.
Yeah.
And our sources draw parallels here to what we've seen in fields like automated machine learning.
Right, where the machines are actually building the models.
Exactly. And the advantages are pretty obvious, right?
Like what?
Well, you have increased efficiency, you reduce human effort, and you get a development trajectory that more closely mirrors how natural intelligence seems to evolve.
So instead of humans having to manually tweak every single aspect of the AI, the system can actually learn to refine its own processes and even its own architecture.
Exactly. It's about the AI learning to better instruct itself and to better organize its internal processes so it can achieve its goals more effectively.
Interesting.
And it's not just about refining existing components. Our sources also talk about this really exciting possibility of AI dynamically creating new tools
Wow.
to further enhance its capabilities for specific tasks.
So it's not just getting better at using existing tools, it's actually inventing new ones.
Yeah, and they're developing metrics to actually evaluate how effectively these agents can do that.
Wow. This idea of AI creating its own tools is pretty mind-blowing.
It is. It suggests a whole new level of autonomy that we haven't seen before.
Yeah. So what are the different ways that these self-improvement processes can happen?
Well, our sources outline a few different scenarios.
Okay.
You have online learning, where the agent is constantly improving based on immediate feedback from its interactions. You have offline learning, where the agent is trained on large data sets in a more structured way.
Huh.
And then you have hybrid approaches that combine both.
So you're saying there are different ways for the AI to learn and improve.
Yeah, it's not just a one-size-fits-all approach.
Okay, and how about knowledge expansion? How does that fit into this whole picture of self-improvement?
Well, our sources explain knowledge expansion as this ongoing process where the agent acquires and integrates new information into its existing understanding of the world.
Okay.
And a really key application of this is in the realm of what they call autonomous scientific discovery,
Oh,
where
wow.
agents can actually generate hypotheses and then design experiments to test them.
The AI is becoming a scientist.
In a way, yes.
That's amazing.
And this relates to the scientific principle that hypotheses should be falsifiable, meaning that they can be proven wrong through testing. And we're actually seeing examples of these AI systems acting as quote-unquote AI scientists, and they're making some really novel discoveries in fields like drug design and material science.
Wow, so the AI is helping us to make new scientific breakthroughs.
Exactly. Of course, there are still some limitations, particularly in areas that require really deep quantitative or symbolic reasoning.
Okay.
And that's where external tools often come in.
Okay, so there are still some things that the AI needs our help with.
For now, yes.
Okay. It sounds like this whole field of self-evolving AI is incredibly dynamic and rapidly advancing.
It really is. It's one of the most exciting areas of AI research right now.
Yeah, I can see why. Now let's talk about what happens when you don't have just one intelligent agent, but you have multiple agents working together.
Yeah, multi-agent
Right,
systems.
multi-agent systems.
Hmm.
So what are the fundamental concepts behind that?
Well, our sources introduce this idea of collaboration and even a form of evolution in these multi-agent systems.
Hmm.
And they actually draw inspiration from natural systems like biological ecosystems and human societies,
Okay.
where groups can often achieve more than individuals acting alone.
Right, the whole is greater than the sum of its parts.
Exactly. And the basic idea is that by having multiple agents interact and coordinate with each other, they can tackle problems that would be way too complex for any single agent.
Okay, so they can work together to solve bigger challenges.
Yeah. And these agents can be similar to each other or they can have different specializations and abilities.
Okay.
And our sources, they categorize these large language model-based multi-agent systems based on how they learn from strategic interactions, how they model and simulate complex scenarios, and how they collaborate to solve tasks.
So it's like building a team where each member brings different skills to the table?
Yeah, that's a good analogy.
Okay, so how do you actually go about composing these AI agent teams?
Well, our sources talk about different types of heterogeneity in these teams.
Heterogeneity.
Yeah, meaning diversity. So they might have different personas or roles, they might have different specific capabilities, or they might even have different action spaces, meaning the types of actions they can perform.
So like in a team of robotic agents, one might be good at navigation, another one might be good at manipulating objects, and a third one might be good at visual recognition.
Exactly. Each agent contributes its own unique skills to the overall task.
Okay, I see. And how do these agents actually communicate and coordinate with each other? What are the rules of engagement?
Well, that involves what are called agent interaction protocols.
Okay.
And our sources mention different message formats and communication channels that are being used in existing systems.
Okay.
And they also talk about some emerging, more advanced protocols that focus on things like agent identity, negotiation strategies, the flexibility of communication, and the degree of centralized control.
Okay.
And the overall structure of the system can be either static, where agents have these predefined roles and connections, or it can be more dynamic, where agents form and dissolve teams as needed.
So there's a lot of flexibility in how these multi-agent systems can be organized.
Yeah, there's no one right way to do it. It really depends on the specific application.
Okay. And how about the collaboration itself? What different forms does that take?
Well, our sources detail all these different types of agent-agent collaboration.
Okay.
Some of them focus on reaching a consensus or an agreement.
Okay.
Others focus on agents learning from each other by sharing their experiences or engaging in discussions.
Okay.
And we also see examples of observational learning, where agents learn by watching what other agents do, and even teaching or mentoring interactions, where more capable agents guide less experienced ones.
So it sounds like there's a whole spectrum of ways that these agents can interact and learn from each other.
Yeah, it's a really rich area of research. And ultimately, the goal is for this collective intelligence to emerge, where the combined abilities of the group actually surpass the capabilities of any single agent.
So it's not just about the individual agents getting smarter, it's about the whole system becoming more intelligent.
Right. And the development of those individual agents is actually enhanced by the interactions within the group.
That's fascinating. It sounds like managing these multi-agent systems could get pretty complex.
It can.
So how do we even evaluate if they're functioning effectively?
That's a really important question. And our sources explain that evaluating these systems requires a shift in perspective from how we assess single agents.
Okay.
We have to focus on the dynamics between them.
Okay.
So they talk about these benchmarks for evaluating how well these systems can solve tasks, particularly in areas like code reasoning and knowledge-based question answering. And they often emphasize the importance of agents being able to use external tools.
Okay.
But beyond specific tasks, there's also this need to evaluate the system as a whole.
Okay.
So looking at factors like the quality of their collaboration, their efficiency, the quality of their decisions, and their ability to adapt to changing circumstances.
So it's about understanding how well the whole system operates as a unit?
Exactly.
Okay. And as these multi-agent systems get bigger, are there any new challenges that come up?
Absolutely. Scaling up these systems introduces all sorts of challenges related to the increased amount of communication that's needed between the agents
Okay.
and potential bottlenecks in coordination.
Right, because the more agents you have, the more complex the communication gets.
Exactly. And our sources talk about different architectural approaches to address this.
Like what?
Well, you have centralized, decentralized, and hybrid models.
Okay.
And they also discuss techniques for optimizing the network of interactions and reducing communication overhead.
Okay.
So the goal is to maintain the system's effectiveness and efficiency, even as the number of agents increases significantly.
Okay, so scalability is a big challenge.
It is.
But researchers are working on solutions.
Yeah, they're making progress.
Now, this is all incredibly powerful stuff, but it also brings up some really important questions about safety. How do we make sure that these advanced AI systems are safe and beneficial?
Yeah, that's the big question.
So what do our sources have to say about that?
Well, they dedicate a lot of space to this topic,
Okay.
and they talk about what they call agent intrinsic safety,
Okay.
which are the vulnerabilities within the AI models themselves.
Okay, so what would be some examples of those vulnerabilities?
Well, one example is what they call jailbreaking.
Jailbreaking.
Yeah, where malicious prompts can actually trick the AI into bypassing its safety guidelines.
Oh, wow. So somebody could intentionally try to make the AI do something harmful.
Yeah, that's the concern.
Okay, and what else?
Well, there's also what they call prompt injection attacks,
Okay.
where harmful instructions are embedded within seemingly normal input.
Okay, so it's like sneaking in a bad command disguised as something harmless.
Yeah, that's the idea.
Okay. And are there any other vulnerabilities?
Yeah, they also cover data poisoning attacks, which aim to corrupt the AI's training data,
Oh, wow.
or even insert these hidden backdoors that can be exploited later on.
So it's like tampering with the AI's learning process to make it behave in a certain way?
Yeah, exactly. And then there are also concerns about attacks that could actually reveal private information that the AI was trained on.
So it's a constant battle to try to protect these AI systems from being manipulated.
It is. And the safety concerns actually go beyond just the AI brain.
Okay.
Our sources also talk about threats to other components, like the perception systems,
Okay.
where carefully crafted adversarial inputs can actually fool the AI into misinterpreting information.
Oh, wow. So you could create an image or a sound that would trick the AI into seeing or hearing something that isn't really there.
Yeah, that's right.
Okay. And are there any other safety threats?
Yeah, there are also safety considerations related to the actions that these agents take,
Okay.
especially when those actions involve using external tools or interacting with the real world.
Right, because if the AI makes a mistake in the real world, the consequences could be serious.
Yeah, that's the worry.
Okay, so this all sounds pretty serious. What are the solutions?
Well, one of the key concepts that our sources talk about is something called superalignment.
Superalignment.
Yeah, and this is essentially about ensuring that the goals of highly advanced AI remain aligned with human values, even as their capabilities far exceed our own.
Okay.
So it's about going beyond traditional safety measures to address the potential for unintended consequences in very complex long-term tasks.
So it's about making sure that the AI is always working towards our best interests, even as it becomes more and more intelligent.
Right, and the research also touches on this idea of a safety scaling law, which suggests that as these AI models become more capable, their potential for misuse or their vulnerability to sophisticated attacks, that might also increase.
So the more powerful the AI becomes, the more important safety becomes.
Exactly. And this really highlights the need for proactive safety research and ethical considerations.
Right, we need to be thinking about these issues now before it's too late.
Absolutely. And it's about finding the right balance between an AI's helpfulness and its safety.
That's a really important point. We don't want to stifle innovation, but we also don't want to create something that could harm us.
Right. It's a delicate balance.
Well, this has been a truly fascinating deep dive into the world of advanced intelligent agents.
It has.
To recap, it sounds like we're witnessing a fundamental shift in AI, with systems that are increasingly drawing inspiration from the human brain, learning in incredibly sophisticated ways, collaborating to tackle really complex problems, and facing these significant and evolving safety considerations.
Yeah, that's a great summary.
And for you, the listener, I think gaining a better understanding of these core components, these mechanisms that are driving self-improvement, the potential of collaborative intelligence, and the absolute importance of safety, that provides a really crucial foundation for navigating this future of AI.
It does. It's essential knowledge for anyone who wants to understand where this technology is headed.
And it leaves us with this really profound question to think about. As these intelligent agents become more and more integrated into our lives, how do we strike that necessary balance between their immense potential and the absolute imperative of safety and ethical guidelines? How do we make sure that these powerful technologies truly serve humanity's best interests? That's a question that we're all going to have to grapple with as we move forward.
Yeah, it's a question that doesn't have an easy answer, but it's a question that we need to keep asking.
Absolutely. Thanks for joining us on this deep dive.
It was a pleasure being here.
We'll see you next time.